And now we're on the last part of this module. So, question is, why is math important in physics? Just in case you don't realize it yet, we were already doing math in the previous sections of this module. But to give emphasis on the last part, um, we have some um, pointers to for you to ponder on. Okay, number one, math is a great way to get a very concise statement that would take a lot of words in English. That's why if you have noticed, for example, we have force. To define force, we can simply say it is the product of the mass and acceleration, or m times a. Okay, so if you see the formula of force, you can easily understand its context or its essence. Okay, so we can say, oh, since it has a mass and an acceleration in its formula, that means it is dependent on the mass of the object and the acceleration involved. Okay. Another thing, math equations tell how physical concepts are linked together. So for another example, the same example, we have the force. Um, F is equals to ma. So we can say that force, or knowing that mass is constant, or given that mass is constant, so we can say force is directly proportional to acceleration, which means if we apply more force, then the object can be subject to a higher acceleration, like what we do in our bike. So when we bike, remember our mass don't normally increase or change when we bike. Okay, what could be changed is our force, the force that we apply. If we apply more force when we bike, then we can expect to have or to achieve higher acceleration. Okay, we can achieve to go faster. Okay, so in that way, we know that okay, I mean force and acceleration are actually directly proportional to each other. The higher the force, the higher the acceleration. Okay. Um, Another thing, math mechanizes thinking, and that's why it is used to solve problems. And um, you will see later on, of course, to compute for our physical quantities, then we make use of math, starting from algebra to, I mean, even starting from basic arithmetic to algebra to calculus. I mean, we all also have geometry and trigonometry, even statistics, probability and statistics, and then calculus, what else? And some other more advanced mathematics. They are all useful and important in studying physics, okay? Especially in solving problems. And lastly, math can be used to make graphical representations of measurements. So, by the way, we have our, if you have noticed our laboratory activities, they are more on graphical, okay? They are meant to expose you to how physics can be viewed in terms of graphs, okay? Or how our physical quantities can actually be represented as graphs, okay? For analysis purposes, okay? And with all of this, we I introduced to you the term mathematical modeling. So for example, if we have a real world problem, we can actually translate that into a mathematical model so that we can provide the right solution. Okay? Or before we can provide the right solution. So to convert the real world problem, we have to define it first and then translate it to mathematical model so that we can analyze, okay? Analyze the what's going on, what are the concepts involved, what are the things that must be changed or adjusted or removed or added. Okay, so we analyze that and then we interpret it. Okay, so in that way we can better solve the problems. Because mathematical modeling is a process of using math to represent, understand, analyze, and predict real-world systems or problems. simplifying complex situations into a solvable mathematical form, gain insights, and make informed decisions. Okay, so you're going to learn more of that in our next modules. For now, our specifically what we the mathematical models that we are concerned of are physical models. Okay, when we say a physical model, we are actually referring to something that replaces a real system with an idealized version that obeys clear assumptions. So we don't know everything. That's why um we can come up with a model to help us make um wise or educated assumptions. Okay, so examples include treating an extended object as a point particle, modeling Earth's surface as flat over short distances, or assuming forces act instantaneously. Okay, so these choices are not mistakes, but intentional approximations. Why? Because we want to simplify analysis while preserving the dominant physics. So any quite negligible things, we can remove them from our model. But take note, the validity of a model depends on the context and scale of the problem. Okay, so for ECEs, especially for those who are in the context of control systems, we have one of the most useful models that we do is the mass spring damper model for our response for determining or controlling how our system responds to a certain input. So as you can see here, we represent spring and uh, dampers in terms of derivatives. Okay, we represent the forces involved in them as in terms of derivatives. Okay, and that's a long story, and we're not going to talk about it yet, but it's just this is just meant to give you a glimpse of what's about to happen in this course. Okay, so note that all models rest on assumptions, which are statements taken to be true within a given range of conditions. So common idealizations include neglecting air resistance or friction, assuming constant acceleration, and treating materials as rigid or uniform. And with that, we are actually doing some approximations. So when we say approximation, we are referring to something that is controlled, um, something that is the controlled neglect of small effects that have minimal influence on the outcome. So normally, when we come up with a result, if our answer or the result is too long, we normally get rid of the less significant portions. Okay, that's why we round off. Okay, so approximation allows physicists to extract useful results when exact solutions are impossible. Okay, so the if we don't do approximation, then we can never have any solution at all. Okay, but remember, approximation is guided by three things actually. Relative size of quantities such as small angles, weak forces. Also, the measurement uncertainty. Effects smaller than uncertainty are often negligible. And lastly, order of magnitude reasoning. Okay. And finally, I'd like to emphasize on these words. So we actually come up with our physical model, and depending on the situation, the physical model has somewhat like it takes a different form. Okay, it has a different purpose. Um, Scientific method. If we follow this scientific method, I'm not going to discuss it. You can zoom it in. Scientific method. Remember, we do that. We follow that if we seek to explain how the natural world behaves, wherein the physical models are used test ideas about underlying laws and mechanisms. Okay. Meanwhile, the engineering design process focuses on solving practical problems within constraints such as cost, safety, efficiency, and materials. And here, the physical models are tools for prediction and optimization, and they are not necessarily used for discovering new laws. Okay, because our goal is to solve the problem, not to understand the the world we live in. Okay, but there are times when these two go hand in hand. These two must be used together. Okay, one is a part of the other. Right, and it's up for you to find out. Right. In the meantime, kindly observe how scientific method and engineering design process work. Okay. And that would be all for this module. Thank you very much for listening. See you in the next one.